Anyway, our next speaker, James Hardesty. One of the most fascinating people I've ever met. He's an electrical experimenter out of Ithaca, New York. He builds demonstration equipment for schools. These are little custom-made electrical machines that can help illustrate principles in classrooms. He's a science historian. And I feel that this lecture is especially important because it's a good introduction to the concepts you'll be hearing tomorrow morning, first thing, from the Coram brothers. So this is a good one to pay attention just because of that. It'll help you understand better what you're going to be hearing in the morning. He also has a classical Chinese education, spent some time in Taiwan, and does Chinese paintings. Here's James Hardesty. Give him a good welcome.
There it is.
Can you all hear me back there if I talk like this with the mic here? Is it good or bad or what? Yes? No good? Okay. There, we go like this. Yeah, well, these things are tough enough to juggle all this stuff around here without having to do this too, but we'll do the best we can. The topic to be covered this evening is a large one, very, very large, and I have sat around thinking about how I'm going to actually do this so that we can touch on a lot of the important areas here and not take up the whole evening. When we consider all of the research done in recent years on Tesla's equipment, trying to solve the, quote, mysteries of the magnifying transmitter and the methods of its Schumann cavity resonance and many of the other things that are being considered, there are a number of methods that have been considered, one of which is the use of vacuum discharge tubes, X-ray tubes, electron gun producing tubes to do this. This is one of the methods that is under serious consideration. Looking at Leland Anderson's slides yesterday, there were quite a number of vacuum discharge tubes that were shown there. I'm sure that the actual number that were made and experimented with probably dwarfs the number that was represented in those slides, but in an effort to lend some historical background to X-rays and their discovery, this will be a historical talk. And the things that led up to that discovery and some ideas which you might want to think about that I hope will lend a good historical background for tomorrow's talks and the work of Jim and Ken Coram and others. We'll present this historical approach. Before I start, I would like to remember two people, one of which is my guru, if you will. Mr. Charles W. Smith, who is deceased for some years, was an early X-ray pioneer and opened his doors to me when I was about 15 years old. And he had a wide collection of tubes, coils, and all kinds of equipment from the turn of the century, and allowed me to go with him and do some of his demonstration shows. And it opened, it fascinated me beyond belief, and I certainly owe a lot to him. And in that vein, I hope to do as well here tonight. Also, there's one other person who is quite with us, although not with us here, that I would like to mention because I think a great deal of us owe a lot to him, and I know we wish that he were here, and that's Harry Goldman. Without Harry, I think a great many of us would still be wondering which end is up and might not even be here. I've tried to convince Harry many times to come out to Colorado Springs without any luck. Nonetheless, I'd just like to mention him here now, and as we all think very well of him, the Tesla Globe Builders Association. The phenomenon of glow discharge or vacuum discharge, of course, has been seen in such phenomena as the northern lights, even lightning discharges and so on. We see some of these phenomena. But the actual scientific, or shall we say observable phenomenon in the laboratory really did not occur until about the year 1675. And at that time, a fellow by the name of Jean Picard of the Paris Observatory was working with a very early type of Torricelli barometer, a mercury barometer. The stream of mercury that was held up in the barometer drawing down was pulling a vacuum in the tube itself. And of course a vacuum at that point was not necessarily something that people didn't know anything about, but it wasn't explored very well. But there was a lightning storm going on, and the charge in the air was considerable, and Picard noticed that his barometer was glowing in the dark, was showing this kind of effect, this purple light was in it. And wondered exactly what that was and didn't quite understand, so he carried it to some different places. As a matter of fact, he finally carried it and put it inside of his home because he was on his way home when this happened, and the discharge stopped. The phenomenon here was not investigated seriously until around 1705 by a man by the name of Francis Hawksby, who was an electrical experimenter and an instrument builder in England. He was an associate of Robert Hooke. And if any of you, I'm sure you have seen static machines, and I'm speaking of the frictional type of static machines, the name Hawksby has got to be something that is well known. Hawksby, having looked at some of the work of Otto van Guericke, who improvised the first reasonable vacuum pump made out of what was used as a syringe pump for firefighting, simply reversed the foot valves in the thing so that he was able to reverse and pump a very rough vacuum with that particular tube and machine, and did a number of experiments, one of which is very famous, where he took two teams of horses and hitched them to two hemispheres, which he put together and pumped a vacuum with his machine. And the horses were unable to separate those spheres, and that was considered to be one of the first and really amazing vacuum experiments. I'm going to go back and forth on this because there are several points I'd like to make as we go along that make the discovery of X-rays possible. You need a good vacuum, number one, so you have to look at that technology. You need a good high potential of electricity that you can supply at a reasonable flow. You have to have good current, and static machines are, in some cases, reasonable, but the induction coil is something that is very much more reasonable to use. And the third thing we have to look at is the actual study and development of vacuum discharge tubes to the point where vacuums and X-rays were able to be gotten together and working. I think I'll start with the slides. Is there a way to turn the lights down here? And hopefully I can see what I have here. I can't see. Well, no, that's okay. I think we need to see the slides. I'll just have to hoof it, as I say. Let's see what we can do here. Okay. Turn the lights down. It's okay. Where are we here? And we all see that. You see that, Jim? Okay. That's good. This is one of Hawksby's machines. This is a basic design of a frictional type static machine. The glass sphere in the center is rotated. One's hand or some silk or cotton material, leather or whatever, can be touched against one side, electrons rubbed off and collected by various brushes on the other side of that tube. What Hawksby did as a real innovation to his earlier works was he pumped a vacuum, a rough vacuum in the cylinder here, and when he rotated the tubes, he was able to, by touching his fingers to them, and even without touching his fingers to them, he was able to get a purple glow inside of the tube. Quite interested in this, he proceeded to go on and make all kinds of glass spheres and all kinds of bottles. You see a few here, but we can move on. See another one. This is another tube where he has concentric vacuum tubes here in which various levels of vacuum were produced, and he was experimenting cranking those wheels and getting as much potential electricity there to ionize some gas inside this tube. And this was a very successful way for him to study the glow discharge. Now the bottle that's on the right is another experiment that he did with the use of mercury, which he did not necessarily associate with an electrical phenomenon at the time. And what he did was just taking mercury, putting it in a tube and shaking it. And as a result, he could get a glow discharge inside the tube. He went a little further and built this particular device in which he employed his vacuum pump as well as a pool of mercury below. And he pumped his vacuum, then opened up a valve. The valve drew in the mercury up, and it splattered on the top of the tube and dripped down the sides, and brilliant flashes of light and so on were produced. He called this mercurial phosphorus, was the phenomenon that he observed here, and what he called it. Well, this type of study went on for a long time. This was something that was part of electrical experimenters. There's another one of his machines, again, a crank machine, for that same phenomenon, yeah. This is, by the way, a picture of Otto von Guericke. I talked about the inventor of the first vacuum pump. The spheres he holds there are sulfur spheres, and he actually produced static electricity by spinning these spheres around in the same way that the glass spheres were spun. The way he made these was rather curious. He took a Florence flask type glass, put a stick down into it, and then poured a molten sulfur into that, and when it cooled and hardened, he merely broke the glass on the outside, giving him these spheres with trunnions that he was able to spin and produce static electricity. Known for a number of experiments. This is another of the Hawksby type machines, but this was owned by Benjamin Franklin and used during his period in the 18th century, in the late 1750s. This is a machine which I actually have touched and I won't say played with, but I spent a lot of time at the Franklin Institute when I was, in fact I still do when I go to Philadelphia, but the machine is not available to be gotten close to anymore. This is a much better view of the machine. And you can see that this is actually specifically constructed for the use of producing electricity, and the crutch type top underneath there that touches the spheres, where the spheres rubbed against, and the arm coming over the top with the fingers reaching down collects the charge. And on the back of the machine there is a copper sphere capacitor to store your charge, and cranking the handle. The machine works quite well. They operate it. They did when I was a kid, but they don't do it anymore. I suppose it's deteriorating and has not been repaired. This is another type of frictional static machine that was popular in the 18th century. Last year at the Antique Wireless Association flea market and symposium, I think the flea market actually is more famous than the symposium for the wonderful objects that can be obtained there. I found underneath a truck in an old box the glass sphere in the center and the trunnions as well as the crank for one of these, exactly the same machine. And for a giveaway price, I took it home, and I'm restoring it because this, curiously enough, as the story goes, Franklin purchased about 10 or a dozen of these from Cuthbertson in London and brought them to the United States and gave them to the various universities, such as the University of Pennsylvania and so on, so that they were able to study static electricity. I would like to think that perhaps this particular one is from that purchase, but I think the machine is so very common that it's hard to say that it's the case. I'll dream, whatever. This is another form of, again, frictional static machine. This is in the Antique Wireless Association Museum, this particular type. And again, this, you see there's a belt on the top of that you can rub the glass sphere against, and then there's capacitive structures there to pick up and store the charge. This was basically the method of obtaining electricity through the 18th century and through the early part of the 19th century especially. And there were many brave and courageous individuals that went beyond this particular step to actually charge Leyden jars during thunderstorms on the roofs of houses and other places in order to get a little electricity to study. Oh yes, this is the Van Marum machine, by the way, which is the greatest of the frictional electric machines. It is in a museum in Amsterdam at the present time. We racked our brains the other night to try to remember exactly what the name of the museum was, but it's the Van Marum machine, which was ordered also from Cuthbertson of London by Martinus Van Marum for experimenting. This machine is an amazingly awesome machine, which gave a 3.5 foot spark from its cylindrical capacitors when working well. It's quite a machine to see, and you can see the work there is quite nice for that particular time. This is another form of kind of a small crank machine, again with these capacitive objects out front here to store up your discharge. And this is a picture of Georg von Kleist, who is actually the first person to experiment unwillingly with the capacitor. Now, there were a number of theories of the alchemists and others of the time and before that electricity was a matter of fluid. And so von Kleist in 1645, thinking that it might be possible to store electricity in a fluid, he got a bottle and with one of these static machines, which is set up here in a rather curious way, which we won't go into, he put a charge into a bottle full of water, and he had his hand on the outside, and he got the electrical charge to go into the water. And then when he was finished, he had an electrode in the top, and when he was finished, he moved away from the machine and quite naively reached over to take the electrode out of the top of the Leyden jar and experienced the first near electrocution from a capacitor. He was not a major figure in the development of this. This is why the form of the capacitor, as we know, go on away, the Leyden jar, was developed by Muschenbroek at the University of Leiden in the early 18th century, and it is for that institution and the work of Peter von Muschenbroek that the Leyden jar has its name and its great history and use. This particular Leyden jar here is in my collection. It's a marvelous piece of equipment. The sphere at the top can be raised or lowered and for different experiments, and these two arms here press against the inside of the jar to make a connection with the inside tin plate. On a good dry day with a static machine, I can get almost a 3-inch spark to jump off that jar without that thing shorting out, which is really incredible, and you can hear it down the block. This is a beautiful piece of equipment. It was made for a Töpfer-Holz static machine in the year 1885. The machine was in fairly bad repair, and I restored the jar itself. An older jar, a Leyden jar, is this kind here. This was the more along with the von Kleist experiments. This is a water Leyden jar. You put some salt water or other electrolyted water inside that, and then put the charge in the top and work the capacitor the same way. This was another wonderful acquisition from one of these flea markets. This was all full of cake, salt, and all kinds of things, and the person at the table thought that it was a rip-off at $5, so I said, well, that's okay with me, I don't mind. So there it is. There are those things around. These are, of course, have a great history, and the Leyden jar, of course, and through the 18th century, there were many brave folks who charged Leyden jars through the use of not only static machines, but if you would put up a rather large rod out above your roof, and during a lightning storm, if you were to take your Leyden jar outside and put it near to the base of this antenna, this vertical antenna type structure, then you would be able to fix a charge in this and take that and use it for experiments. It was a matter of fact, it was this kind of experimentation that actually led Galvani and subsequently Volta to put together the electric battery. Moving on, this is a very basic late 19th century induction coil. So for a few minutes I'd like to talk about this particular machine. Stepping back a minute, of course, there are a number of things that have come together in order to see this particular scientific marvel come to pass. First of all, the invention of the electric battery, and without that, this could never have happened. But more than that, the observation of Ørsted in 1819 of the deflection of a compass needle while passing an electric current through a wire, and subsequent works of Sturgeon and other people wrapping many turns of wire around and getting different effects, stronger effects of that needle deflection. And eventually, the observations of Faraday, looking at going from electricity to a magnetic effect, and then the idea of coming back the other way and producing electricity through magnetism, magnetism through electricity. This idea of mutual induction and so on that Faraday experimented with resulted in this particular piece of machinery, without which, of course, experiments in X-rays could not have happened. Actually, the first very successful induction coil was invented by an American, although everyone who speaks of induction coils will talk about the Ruhmkorff coil. And actually, Charles Page, in about 1836, 1838 or so, built the first multi-winding, pancake winding induction coil, looking at a number of people, Faraday's work plus the work of Sturgeon and Henry and others before him, realizing on Faraday's observations about electromagnetic induction that, of course, if you just connect a direct current to this machine, you will get nothing but a magnetic field, and you will get no step-up of current. You have to make and break the electrical current in this machine to get it to work. And so, of course, originally one of the most creative ways that they started with was to get an old file and a piece of wire and simply bring the wire, rub it down the file. And during that process, there was a make and break effect going on, and you were able to get a small spark across the secondary of the coil. Page's innovation was to take a wheel that looked like a regular cross-cut saw blade for an electric saw and simply put a copper strip above that, so when you turn that blade, he would get a make and break effect in there. And he actually observed quite correctly that it was very important that the make be longer than the break, so that the magnetic core of the coil was able to be charged up enough, and that when the break occurred and the magnetic field collapsed, that he would be able to get a pretty good spark across the secondary. And that technology was developed by others, McNeff and so on, as years went on, so that they actually put together this hammer brake, which is just like a doorbell buzzer that we know well today. And that actually brought this into fruition as a machine that was reliable and so on, this hammer interrupter that was used. At that point, Ruhmkorff, who was a very creative individual, realizing that there were a number of parameters necessary to make induction coils very successful, the most important one of which was insulation. If you've ever experimented with induction coils, you will come quickly to realize that you can build a very large induction coil with many, many turns of wire, and you can have a very good interrupter, and you can build a lot of things correctly. But if the insulation between the primary and the secondary is not very good, then you cannot get the kind of voltage across the secondary that you might need for your experiments. So Ruhmkorff was the first person to use an actual glass pipe, which he ran down here. This was about a 3/8-inch glass pipe that ran all the way down, which separated the primary and the secondary, and this actually worked very well. And then his subsequent experiments with hammer interrupters that were weighted and slowed down and all that, he was able to produce induction coils with considerable sparks. And by 1850, he had coils that were producing a spark of about, I think 16 inches is what was happening at the time. This is a spark that is generated by this particular type of induction coil. This is a coil that was brought in for a photograph by my friend Lauren Peckham from the Antique Wireless Association. This is a beautiful coil. It works extremely well. You can see on the right-hand side is the hammer brake, polarity switch, and so on, the windings, the insulation that's set up here, and of course you have porcelain handles and discharge spheres. This was a coil that is extremely popular. I've forgotten the manufacturer's name. It's made in Britain, about 1890, and found it was produced a lot, was used by doctors for X-ray equipment. as well as for early amateur radio operators, and the coil could work very well both ways. There are some considerable differences in coils if you're going to use them for wireless work or for medical work, but this was a very standard, inexpensive, and very good quality coil that could be used. Building induction coils is really an amazing thing. If you've ever been to the Science Museum on, I guess it's Cromwell Road in London, you can see the great Spotswood induction coil over there, which is a very large coil, built on the same principle, but was able to produce a 44-inch spark. And it was one of the largest induction coils that was ever made. It's quite a thing to see, and it was always the pride of laboratories at the time to see exactly how big a spark your induction coil could produce. And it was a matter of, ours is better than yours and our team and so on. So I suppose our friend Mr. Tesla coming along with a much more efficient system, producing sparks that would dwarf these machines by, tremendous amounts, was quite an interesting effect at the time. This, now another very effective voltage production unit that appeared in the late 18th century was this is another static machine. This is a Tuckler machine. In about 1775, 1780, in England, a gentleman by the name of Bennett, observing the inductive quality of static electricity, came to develop something called Bennett's doubler, which he could move static charges back and forth between capacitive structures and keep building up a charge, which once that idea became developed, and it's a rather simple idea, this new breed of static machine came about. And the difference is that the earlier machines that I showed were called frictional static machines, whereas this particular machine here is referred to as an influence machine or an induction machine. Very basically, the way that it works is, could get involved, but I'll just say that this neutralizing rod across here, when one of these electrodes is parked here and parked here, what it does is the charge that is found down here, of course, will, if there's a positive charge that's induced or actually touched by a brush, you get a negative charge to appear over here, which will be put onto each one of these particular spheres, and the subsequent discs that are in back of it, an induced charge, will be put on those, and then various forms of rotation and development will keep passing these charges back and forth, and as Lord Kelvin described it, it's like compound interest. If you ever use one of these machines, you start to crank it, you don't get any result out of it, but after a second or two of cranking, then you all of a sudden begin to hear the hissing of the corona discharges. The static charges builds up until it breaks across the electrodes. This was a considerable competition for the induction coil, and it existed in some forms before the induction coil's development, really serious development. The only problem with these are, of course, the weather does play a considerable fact in the use of these machines. And if the weather is extremely humid, like it is in the part of the country that I come from, at this time of the year in my laboratory, it's all you can do to get this thing to just whisper to you. There's no way. So they were finicky and difficult to make work. The most successful of the static machines was the Wimshurst machine, which this is a version here. There's a little Central Scientific Company Wimshurst machine down here, which actually has 12-inch discs. This machine is 7 feet tall. I forget exactly where this one is parked. Someone told me the other night what museum has this. But you see, bigger is not always better. Because you would say, gee, this is this huge machine, and wow, it must produce a huge amount of electricity. Well, the difference and the reason why a larger machine can produce more electricity is because the limitations of a Wimshurst machine or a Holtz or a Tuckler machine is the insulation. And if you have huge voltages on these particular spinning plates, if they can arc back to the center and arc over to the other side and jump across and through the electrodes and so on, the machine will break down, and that's the voltage limitation on them. You can just, so that the bigger size is for better insulation so that the process can work better and you can store a larger charge without it breaking down. A.D. Moore, a genius who was, I guess he recently passed away, wrote a book called Electrostatics talking about the production of his newer development of these machines called the die rod machines. The particular die rod machines have even better insulating qualities and can produce even better voltages, but they were not, his method is really a fantastic method to use. This is the kind of a machine that you would see in the latter part of the 19th century. Now, I was just telling Bill Weissock the other night that I just gave away a machine like this to the Antique Wireless Association, and he told me that he was sorry that I had done that, and if I happen to find another one floating around, that I should call him immediately, which I will do. But they don't actually pop up too often, except I do live in Ithaca, New York, which is near Cornell University, and they have a trash fetish. That is, they seem to, if it isn't, within the last year or two, it has a tendency to be magnetized toward the trash dump. And there are a whole group of trash pickers, of which I am one, who drive around the university in back of nuclear studies, in back of the electrical engineering building, back of the high voltage laboratory. You make your rounds every few days before the trash trucks come, and you would be amazed at what you get. This particular machine here, I was picking my wife up when she was working some years ago for the English department, and I noticed at the end of the corridor when I was walking in the building, I said, that looks like a Holtz machine down at the end of the, that's not possible though. But it turned out to be a Holtz machine on the way to the dump. So I liberated it from the building, and it needed a lot of work and repair. The one I had has 24 discs, so it puts out a whale of a spark. This is exactly like the machine, which now is at the Antique Wireless Association Museum being restored. That's in Holcomb, New York, a wonderful museum to see if any of you get back that way. These machines were produced and sold and used pretty much by doctors up until in the 1890s. And you can well imagine that if you went to the doctor in 1885 complaining of whatever, not knowing very much about electricity, and the doctor brought you into a room and sat you down under a machine and told you that your troubles were over, and subsequently began to crank this machine around, and you see the results here. I imagine that if it had nothing more than pure fear, you might want to believe that was true. So the placebo effect, if not the vaudeville effect of these machines, is obvious. And but I have to tell you that to experiment with these machines and to see them run, the effect on you is equally the same. It's really thrilling because they really work. And let's see what we have here. This is another version of the Holtz machine with all kinds of attachments, run by a motor, of course, so you can get even more out of it. This is the actual machine operating. And you can see the brushes down here. This particular, the Holtz machine is a bit complicated, but look at that. Here's your Leyden jar. And some, I suppose, calcium chloride or some bottles in here to keep the moisture. The machine is sealed in glass inside. Large capacitive spheres here, and I believe that is about a 12-inch discharge. You can tell the poles by the formation of the discharge. That's quite a healthy discharge, and in fact, as we will see as we go along, these machines fell into quick use by the X-ray pioneers because they were, to some extent, quite effective, provided that weather allowed you to use them. This is a close-up view of that discharge. Do you see any fireballs in there, Jim? That's quite possible. I don't know. This is a rather noisy discharge, too, because it is somewhat capacitive, of course, from the spheres it's coming from, and that's quite a spectacular thing to see. I don't know of any working static machines of this kind anymore. I remember as a kid in Philadelphia, there was a machine that was thrown out from the Pennsylvania Hospital about 1963 or something that I missed getting, which belonged to a famous doctor we'll talk about a little later on. Okay, so we've discussed a few issues of high voltage from the static machine side and from the induction coil side, and we'll go back to that a little bit. The next thing I want to discuss is vacuum technology in the 19th century. Now, we talked about Van Gurica's work, and there were a number of mechanical pumps produced all through the 18th century and into the 19th century. If you look at these pumps, you would realize that if you want to experiment with cathode rays, if any of you have a bad back, as I do, you would abandon the study immediately because you would have to spend weeks pumping these things because of the seals and so on. You'd never be able to get down to much of a vacuum. And of course that changed a bit with the invention of this machine, which is known as the Sprengel vacuum pump system. Now, back as far as Torricelli and the barometer, and experiments done over a period of time with mercury drawing down on a closed tube, vacuums could easily be produced to some extent. Experiments of William Morgan in about the latter part of the 18th century, in his descriptions to the Royal Society, the colors that he produced in the tubes of his mercury lift pumps, as they were. He boiled the mercury and went through all these amazing procedures and described the apple green glow that he was able to get in the top of a very long tube that he had, and he had wrapped the top with tin and then cranked a static machine up and was able to induce voltage to this, and he described this apple green glow that he saw, at which those of us that deal with antique X-ray tubes and so on realize is something that results from the production of cathode rays. So he achieved a pretty good vacuum. But by and large, that was the only system that ever really got that far by his description. Normally, to pull a vacuum, and up in, I guess, around the 1850s, Geisler, who we'll talk about in a minute, had built a pump that used a reservoir like this. You would pick up the reservoir, and the mercury would run down and go up in the tube, and then you didn't have all this, but the mercury would go up in the tube, and then you would simply close off a stopcock, and there'd be another you'd open that would go out to the vessel that you wanted to evacuate, and then you would simply lower the bottle and allow the mercury to pull down and pull the air until it got down to the bottom, and then you would open and close the proper stopcocks, raise up the reservoir bottle, and proceed with that same process, a rather laborious process of evacuating a tube, but it does work. This particular process, invented by Sprengel in about 1865, shows that the observation of how an aspirator pump, I believe they call it, works, is that if you, I believe the aspirator pump is where you run a lot of water down a tube like this, and then the tube comes in up the top there will be a vacuum pulled in that tube, and you can pump liquid and flush the whole thing out the bottom. That was the forerunner of this particular operation, in which the mercury is brought up over the top and it drips down the tube. This particular fall tube here is much, much more narrow in bore than the earlier larger tubes that the mercury was put in. And each time it drips down here, it can take a bit of air down with it, and the motion down the tube of the smaller droplets takes a lot more air off the side of the tube, and a lot more of the mercury is cleared through the tube, and there are fewer problems with mercury vapor and so on. This particular type of pump here, invented, I say, in 1865 and considerably improved on by Crookes and others after him, was the pump system that was used specifically by X-ray pioneers and glow discharge and vacuum tube experimenters all through the latter part of the 19th century. This was the system. There were many improvements made to it, different types of traps and multi-fall tubes, and even a system that was invented where the fall tube was actually put on some kind of trunnions and spun around, so that I don't know how they managed to seal that up and pump the vacuum with it, but they were able to spin the fall tube around, and that spinning, of course, increased the flow of mercury. They could move a lot more air much more quickly. That was a later invention, I guess, in the 1890s, so most of the experimenters, of course, used this particular type of vacuum pump. This is an example of an early Sprengel type system with some improvements. It's actually not a very good slide, but it does show some of the operation. There's a better one in here. Yes, here. This is a classic photograph here. Everyone knows who Uncle Napoleon is there, and our friend Mr. Edison. In the background is another rather curious enigmatic figure by the name of Clarence Dally. If any of you have ever heard of him, we'll talk about him. This is a really good example of a Sprengel pump. Here's the mercury reservoir up top here, the mercury coming down. Here's the fall tube, with just a simple stopcock and so on running over here. Here's the glass tube running down into this box in here where there is an early form of an X-ray tube. And of course, Dalley's hand is on top of the box, and Edison is looking through his invention there, the fluoroscope, at Dalley's hand. And you can see the process. Unfortunately, Clarence Dalley, as we will talk about a little more, was the Edison's glass blower. And if you want to experiment with vacuum tubes, you have to have a good glass blower. Dalley was a genius and was able to do almost anything that Edison wanted, and made a lot of different experimental tubes. And unfortunately, he also manufactured a great number of X-ray tubes when they became popular. And as we shall talk about a little more in the future, the way you test an X-ray tube in the factory is that you put it on the pump, you bring the vacuum down, you turn on the induction coil, put your hand up, take a look at the penetration of the X-rays. Well, that's not quite enough. Okay, turn the induction coil up, pump it some more, and then put your hand back up there again, take another look. Well, that's looking better, do it again. At any rate, the point is that it isn't long before you can get some considerable X-ray burns. Moving back to Geisler, this is Anton Geisler. Around in the 1850s was an amazing glass blower who worked at the University of Bonn, and he had a great number of vacuum tubes that he had made in this particular style. This particular thing he had with his own vacuum pumps, able to pump these things down and get all kinds of beautiful displays. And they were extremely impressive. This was the basic glow discharge phenomenon that was available to him. He used uranium glass, lead glass, soda glass, all kinds of different glass to get very many different effects on the tube. This is the glow properties of the tube. You can see here. This particular tube is present here tonight, and Ken, if you would just hit the coil on that, we can take a look at that tube as it actually is. If you can see that, maybe better on the thing itself. That's the particular Geisler tube, as it was called. Geisler manufactured a tremendous number of these, pumped them down with his vacuum system, and used them for a lot of displays. He was not only a glass blower, he's a very amazing scientist as well, worked at the university, and one of the people he worked with, Julius Plieker, a professor of physics at the university, observing his equipment, asked him to make him some more of these tubes of different styles and so on, which he experimented with, and made some very amazing observations about this glow discharge. This is another one of these tubes here. This is in operation. Thank you, Ken. And you can see some very curious negative electrode phenomenon here, and it's not too clear, the positive column, so we'll talk about that. But this is a very beautiful display that was done here, and here's another one. These are all, people really went wild with these because they're very, very impressive, and here's another one. Okay, the phenomenon of glow discharge we're talking about here that Geisler first experienced, and this is just a simple double-ended vacuum tube here. There's an electrode here and here, the other end. By passing a high potential of electricity through this, we can observe the phenomenon of glow discharge, which really is a phenomenon of the axial movement of electrons and ions going back and forth through this tube, and having excitation collisions as well as ionizing collisions and creating this particular process of discharge, which we will roll through here quickly. You can see the tube a little bit better here. A great deal of conduction taking place here, and ionization, so on, producing that particular color response. I'm not going to we're not running along as quickly as I thought we would. I'll try to go through these quickly. This is, you can see the Faraday dark space beginning to form here. There's a better example of what is known as the Faraday dark space here, named simply because Michael Faraday in his experiments in the 1830s with this particular type of equipment first noticed this particular phenomenon here, the Faraday dark space. This is about 10 torr of vacuum. Here is another example. You can see what is called the cathode glow here, and a very small example was the Crookes dark space. We'll explain that a little bit more. Positive column running down here. Faraday dark space, a bit larger. There it is, much, much larger. And you begin to see basically all the components of the glow discharge in here. This is you can see the cathode glow. There's the Crookes dark space. This little area here is called the negative glow, the Faraday dark space, and what is known as the positive column. These are phenomena that are part and parcel with the movement of electrons from the cathode moving forward, not being able to ionize or excite anything by their speed as they immediately leave there, but within a very short distance from that, which you really can't see the Ashton dark space, but the cathode glow occurs as soon as they can begin to excite the molecules of air in the tube. Moving a little further, when their speed increases in the field, there becomes a dark space that begins to occur because they're ionizing at that point, and the ionization does not produce anywhere near the light that the excitation produces. This is a phenomenon here called the striations in the positive column. And again, here you can see this Crookes dark space in here, which is really the engine of this particular kind of discharge, because it's in here that ionizing collisions produce positive ions, which in turn are accelerated back, striking the cathode, producing secondary electrons, and holding a steady state here of electrons being produced so they can run down the tube. They slow down, and there's darker and lighter spaces as their speed changes. If they can excite molecules, then atoms, rather, they produce more light. If they're ionizing, there's much less light. If they slow down enough where recombination takes place, the spaces get darker. So there's these different striations as the speed of these electrons changes. And on here, there's an even better example. In the early days, the level of vacuum was measured by the size of the Crookes dark space, because as it gets larger, the vacuum is lower, and there was actually a comparison able to be made there about how that worked. Here we go again with, as the vacuum increases, this dark space becomes larger, and the elements in the positive column down there become larger. That's a little better look at the apparatus. That's a much longer exposure. The vacuum pump, the induction coil down below there, you can see the electrodes. Okay. Now, Professor Pleeker of Bonn University, working with Geisler, investigated, found out that as the vacuum is pumped even lower, the Crookes dark space expanded a lot more, the tube became darker, and there was a very curious phenomenon coming from the negative electrode of the tube. There was a curious light. As a matter of fact, he called it cathodic light. And scientists of the time were convinced that it was another form of a movement in the ether. It was a light, some kind of light that was moving along. Even in the time of Pleeker's experiments, he even took a magnet and put it near his discharge tubes and noticed that this light that was coming from the cathode at lower vacuums could be deflected by a magnet. Experiments were done by his student, Hittorf, who was a contemporary of William Crookes, Hittorf, of course, being German at the University of Bonn, and Crookes being a most amazing scientist in Britain at the time. Many experiments were done, of which this was a very important one that both Hittorf and Crookes experimented with, which was wondering if it was possible to focus this particular emanation from the cathode of the tube. And by using this focus cathode, this concave cathode, they were actually able to focus the point where this emanation would strike. It is very important, like we say, about 1865, and at the point of 1865, both Crookes and Hittorf were experimenting with these tubes, is that vacuum pump, the Sprengel pump, came out, which enabled them to get down to vacuums where the phenomenon of cathode rays, which we're going to take a look at here, could be produced. This was one of the first experimental tubes that they had, and of course the beam was focused on sometimes a piece of mica also, or a piece of platinum or tin or other metals. Curiously enough, they were very quickly melted, made molten by the impingement of the cathode rays upon the metal. And also was discovered, and I'm moving very quickly here, but we're running out of time, and there's a million things to say. This is the famous Crookes tube, a phenomenon observed both by Crookes and Hittorf, was the fact that the emanations from the cathode, if you put an object in between them, you could cast a shadow behind that object on the wall of the tube. Not only here, but depending upon where the vacuum was, even sometimes down by the cathode, depending on what it looked like, you could get different shadows cast on the various parts of the tube by virtue of this emanation. I keep talking about an emanation from the cathode because there was a lot of controversy at this time about exactly what that was. Was light a wave or was it a particle? Now we know today that it has both those qualities. We can consider, in those days there was a kind of a war going on, a disagreement between the German physicists and the English physicists about the nature of what these particles were. Of course, Faraday earlier on, considering electrolysis as well as considering this process here, talked about the idea of flying particles, radiant matter, and Crookes, looking at this particular thing and seeing the various effects that took place with these discharge tubes, immediately appreciated the fact that these were some kind of particles, some kind of corpuscle, some kind of actual particle that was emanating from that cathode and creating a specific effect. But there were many scientists who said that it was only light, and there was a lot of controversy going back and forth about that. This is a Crookes tube in our collection, and it shows, let's see if we can get a better shot of that. Yes, this is very curious. If you can see this here, notice that the iron cross in the tube here is kind of just drooped over and down because somewhere along the line with the experimenters with this, they turned on the electricity, the induction coil, and let that run a little too long, too much current, and melted the Maltese cross so that it drooped down. And it no longer casts that same shadow on the wall of the tube. Curiously enough, all of these tubes at this level are producing X-rays, but at the time, no one was really aware of it. Now, there was many experiments going on back and forth between Crookes and Hittorf. A lot of things were being done. Cathode rays had many properties that were really incredible. Inside of tubes, they put gemstones. They put different kinds of salts. They put mica, they put everything imaginably, flowers, anything they could put in there to try to see what would happen, what the effect of the cathode rays would be on them. There are many studies done, but I think that the most significant of the studies, and we're talking about Crookes' work right here, was the magnetic deflection of cathode rays. By taking a magnet and moving the rays, by causing them to be deflected at different parts of the, let's move down here one more, take a look at it. Yeah, this is a better example of one of Crookes' main tubes for experimentation. It's a little window put in here. The cathode rays come down, go through the window, and move along. There is a scale down there, so you can kind of take a look at exactly what kind of sweep is occurring. And this shows what effect happens when you bring a magnet, whether it be a regular electromagnet, near the bottom of the discharge tube. You get this effect, and we'll see shortly how important this was when the final controversy about the electron and the cathode rays was laid to rest by Thomson in 1897. This is a tube in operation showing that exact effect. This is on the tube that used to be produced by, I believe, a Welsh scientific company in the 40s. Can't get these anymore. Have to make your own. Here is another famous experiment that Crookes did. Now, Crookes is famous for the development of the radiometer, and he built, and of course this is a different process, and along with that, Crookes, here's your cathode ray beam is going to get down here. There's a little bit of a mica wheel on here with veins of mica sitting here. Crookes turns the current onto the tube using a magnet, draws this particular, this is made of metal, draws the cathode rays so they bend down and actually touch onto the veins of this particular discharge tube here and causes the veins to spin around. Believing that these were particles, he believed that that was would be an interesting proof that they worked. Here is a drawing of that kind of a tube that was common in laboratories for the discussion of that particular type of work. Here is a real one. Not a very good picture, but you can see the veins that run along those railings in there opposite the electrodes. Here is one that is part of Lauren Peckham's collection again. And this is actually turned on, but you really can't see the effect because I'll tell you, taking photographs of discharge tubes is something else. A lot of times to see it work, but the paddle wheel here will roll along down this end, and you reverse the polarity, and the wheel will roll back. Beautiful tube. This is another experiment that Crookes did in dealing with the particular nature of cathode rays, to have two cathodes, two windows, particles going down the tube, noticing that since they are of a similar charge, they seem to repel each other as they go down the tube. This was a common experiment. And another one here in which he put the electrodes on the outside walls of the tube to produce the same effects. And the reasons why he did this, I'm not going to go into the entire operation here, it's too complicated. This is a tube that, that's another long thing to discuss here. The Goldsteins work in the 1880s with positive rays. This is a tube showing actually the ion beam coming down. There are holes in the cathode here so that those ions actually go through the cathode and enter into the back of the tube here. So then the negative electrode, the positive electrode, here's the discharge up here, but the canal rays or the positive rays come back down into this end of the tube. This is controversy raging about what was going on with these particles, whether they were particles, whether they were light waves. Experiment by Perrin in the 1880s. This is a Faraday shield grounded, and the cathode rays come through, go in and put a negative charge on the cylinder inside, which is connected to the electroscope to detect that negative charge, showing that another proof that the cathode rays have give a negative charge. This is J.J. Thomson's famous experiment, and what he wanted to do here was prove that it was specifically these cathode rays that made the experiment. So there's actually a piece missing here. Cathode rays are generated, go through this. A magnet is used to bend the rays so that they go into that same Faraday cylinder, into the inner tube here, and is hooked to an electroscope so that only when the cathode stream is bent into the tube like that, it works, showing further the specific operations of the experiment. Talk about negative charge. Try to move along as quickly as I can here. This is the most famous of Thomson's experiments, and the tube that he used to do his famous charge to mass studies and weighing and checking the speed of the electron. What he did is, Hertz tried this experiment earlier in the 1890s and failed. And the reason why he failed, again, was because of his vacuum system was very poor. So poor, in fact, that he was not able to get enough of a vacuum in here that when he put an electric charge across here, there was still too many molecules in the tube so that the charge actually was carried off, ionized by the cathode rays in the tube, and he could not get any kind of a deflection here from an electric field. But Thomson, again, realizing that there definitely was a possibility of running this experiment and what it would prove, took the same tube and pumped the vacuum much further down, and the experiment that he produced, if I can get this right here, cathode rays going through here, he had external to this tube, he had an electromagnet, and he would put a certain amount of current in that electromagnet, measurable current. The cathode stream would be deflected on that scale up there. The deflection would be measurable. Then he would put a charge across this particular capacitor, whatever, in here, and he would then equalize the magnetic deflection back to exactly zero. And by doing this, he was able to get some kind of an electro and magnetic relationship to the deflection of these cathode rays, with which he was able to take a look at their charge, mass, and speed relationship, which is a rather simple mathematical study, but a very ingenious method of looking at this. And with that information, he was able to determine the charge to mass ratio of this particle, his corpuscle as he called it. And as there were, through electrolysis, there was that particular charge to mass ratio was available about the hydrogen atom. And through Thomson's studies, he realized that this particular corpuscle particle here was the charge to mass ratio was as much as 1,000 times greater than the available information, which was well known about the hydrogen atom. So he was faced with the issue that either the particle the charge was extremely large on the particle, or that the mass was extremely minute. And of course, this was a very revolutionary concept at the time, because people thought that the atom was the smallest thing that there was. And in fact, this, along with other experiments of his, did show that in fact the electron existed. So this was the tube that the experiment was the birth of the electron, came out of that particular work. Oh boy, so much to do here. I'm going to let that go. This is a Leonard tube. That's a lot to talk about. Let's move on to what this is. Let's go over to Rankin's work and finish up here. Sorry to keep you so long. It says here, and this is another controversy because it's not necessarily true. It says Hittorf tube, with which Röntgen discovered his rays. Quotes Hittorf tube here, focused cathode. There's this aluminum and metal here to do the experiment, but it also, as they found out, produced X-rays and fluoroscopy. Another examination here. That's a wonderful way to treat yourself to a good X-ray blast. To do that how many times a day? Here's the same setup again with the patient, patiently waiting for his X-ray to be taken. Probably took about 15 minutes or something with the film at the times. Another, actually, we were talking about this last night. This is, well, I'm not sure. This is, looks to be some kind of a mercury brake interrupter for the X-ray machine. I'd like to get into that, but we won't. The brakes are really so important for Tesla coils as well as here. But we felt that this is actually a Tesla oscillator run by some kind of a alternating current system in the tank circuit, or at least the capacitor and so on down here, but that isn't definite. But it certainly looks like the equipment like that at the time. It's another picture of the same kind of thing. And this is a picture that I actually took a candid shot of my friends Jim and Ken Coram in their laboratory, getting out of the way of some of those good old fireballs. And yeah, I believe it. No, you know, you know. At any rate, I have run through this like, well, whatever, and I've taken a lot of your time. I have put a bibliography in the bookstore down there Steve is selling. It's called a late 19th and early 20th century bibliography for electrical experimenters. If you're interested in the things that I have run through here, I have put together the available books on the topic, as well as a number of books discussing how to build this equipment, how to experiment with it, where to find the different references and so on. Most of there's about 148 entries in there, along with some very curious advertisements from induction coil makers and X-ray and vacuum pump companies of the turn of the century. There are so many things to discuss here. I hope that in some ways this brings to you an idea of some of the things that happened, the discovery of X-rays, and a few ideas. I know this is so much to say, but at any rate, I won't hold you any longer. Thank you very much for your kind attention.
Make your own tubes?
I have a glassblower friend who does, yeah. But I vacuum them and do that kind of stuff. I will be available, I'll be here until Sunday, and I know that there is a social wine and cheese and some things to do, so if you have any questions, perhaps considering the time and all that, I will make myself, I'll stay here, but I'll make myself as available as I can with a few things I might be able to tell you.
You were asking about that transformers.